Let's go through these properties of the definite integral. There are just a few of them, but you need to make flashcards over them, or you need to make sure that you understand them so that you can apply them if you need to. We will be seeing questions, especially theoretical questions, where you have to know these properties of the definite integral. So make sure that you know them. The first one says the integral from a up to a of any function f of x with respect to x will always be 0. And if we'll think about that, remember this says to start at a, add up the area of all the rectangles over this x interval, infinitely many of them, to get the exact area in the plane. Well, if we start at a and we end at a, well, we don't have any width, right? So our width would be 0 in this case, and 0 times any height is going to be 0. So if the upper and lower limits are the same number, then the integral will equal 0. So make sure you know that one. Here's the one that I gave you in the last video. If we accumulate from a up to b, we always want to make sure that we're accumulating from a smaller x value to a larger x value. If we need to, we can reverse the direction in which we accumulate by switching the limits of integration and putting a negative out front. These two things are equal. We can accumulate from left to right, starting at A, stopping at B, or we can accumulate in the opposite direction, starting at B and stopping at A, and that will give us the opposite sign on our accumulation. So remember that. If you need to switch those limits of integration, all you have to do is pop a negative out in front of your definite integral and swap your limits of integration, and then you can go on about your business. Just as in derivatives, constants pop out front, that's true for integrals as well. So pop those constants out front and get them out of your way. We've already done that in our indefinite integral work, so it shouldn't be strange to us to do it in our definite integral work. It is true that integrals break up over addition and they break up over subtraction. So additionally in 4, you could go ahead and write that if you wanted the accumulated area that was trapped in the plane and it was the difference of f of x and g of x, where it's f minus g, then you could take each one of those functions separately and you could find the area under f and subtract from it the area under g. So integrals break up over addition and subtraction just like derivatives do. So that's pretty handy. It turns out that you won't see as these properties that integrals break up over multiplication or division. Because remember, in essence, what we're doing is we're working our way backward. On the indefinite integral, this was the derivative, and we found the antiderivative function, remember? So there's a direct relationship between derivatives and integrals. So if we found the derivative using the product rule, then we're going to have to use something that undoes the product rule to find the antiderivative, or to take that step back. So integrals do not break up over multiplication or division. Now this has to do with our intervals of integration, and this has to do with the fact that I can add up this area and I can add to it adding up this area, and when I take the area 1 and add to it area 2, that the total area will be the sum of those areas. And so since we would start here at A and stop at B for area 1, and we would start at B and stop over here at C for area 2, it makes sense that integrals, the limits of integration, we can break our integrals up over kind of any interior value on an interval that we want to. It is true that if I find the area from A up to B and add that to the area from B up to C, it's going to give me the total area. So the idea here is we would call this like area 1 and this is area 2. When we add them together, we get the total area starting at A and stopping at C. And you can kind of see that here as well. The area from A up to C can be broken up over any interior point. It doesn't have to just be right in the middle, kind of like this example shows. So make sure you understand this is a property of any definite integral as well. let's take a deeper look at what the significance of accumulated area between the curve and the horizontal axis is. Why is it important? Why is the accumulated area in the plane the output of the position function when we're looking at the graph of the velocity function? Why is the area under the derivative curve the output of the original function? Well, I'm going to go into one context. I'm going to go into the position, velocity, acceleration context, because we understand that relationship, velocity, I don't know what I'm trying to spell there, and acceleration. We understand that this is the original function, the derivative function, and the second derivative function. So if it's true here, then it better hold true in general for any set of functions that have this relationship. So remember, way back from probably your science work in high school, in lower level science, you were always taught that distance was rate times time. So that's what I'm using here. I'm calling distance d, which we understand is position, right? That could be our position function. And rate is our velocity, and time is, of course, time. So since the position is the velocity times time, then let's go to our rectangle example here. If we have a width and we have a height, then the area of that rectangle is going to be the width times the height. And that's all we're really doing. We're saying that underneath the curve, that is our velocity function, over time, here's time 1, here's time 2, if I was to add up the area that's trapped under the velocity curve, or in between the velocity curve and the horizontal axis, that is going to model the position at any time t of that particle, that object, that bag of rocks, that whatever it is that's moving in the plane that has a certain position with the given velocity graph over time. So this is kind of sort of a specific context, but hopefully that kind of helps you understand why accumulated area in the plane underneath the derivative function gives us outputs on our original function. All right, so let's look at some more attributes or properties of definite integrals, and then we'll finish up with an example, hopefully by the end of this video. Hopefully we won't have to have another one. All right, so in particle motion or object motion or anything motion problems, there is a difference between displacement of that particle or object and the total distance traveled by the particle or object. And we can track that difference by what we do with adding up the area and the velocity function. So the signed area turns out to be displacement, and I'm sure in physics you guys have talked about distance versus displacement. Displacement is how far away from the beginning, right? How far away from the beginning was I when I stopped? And with velocity, we know we're moving to the right when it's positive. We're moving to the left when it's negative. So if displacement is concerned, my distance, the distance that I've traveled, is a whole lot of area. But all of this negative area undid the distance. I went back in the opposite direction, right? And so displacement's going to look very different than distance. So displacement is we take into account negative and positive area. The negative and positive areas count. So the sign to the area matters. To the area matters in displacement. And you can see here in distance, we're just worried about all area as if it were positive. We're going to add this up, and then we're going to add the opposite of this up. So we would take area 1 and we would subtract area 2, because the result of that is it's going to be like we're adding area 2, and then of course area 3 is positive. So in this example, I hope you can see that the accumulated area trapped in between the velocity function and the horizontal axis taking signs into account will give you how far away from the beginning here that you were when you stopped moving. That's displacement. If you count all the area as positive area, or you take the absolute value of velocity, which is going to take anything that was negative and flip it over that horizontal axis and make it positive, right? This is what distance, total distance traveled, would look like. So make sure that you could understand the difference there. And just like we have a relationship between displacement or distance and velocity, there is a relationship between acceleration and velocity. Because we know acceleration is the derivative of velocity, then the integral of acceleration will give us the change in velocity from time 1 to time 2. Just like the integral of velocity gives us the change in position from time 1 to time 2, the integral of acceleration gives us the change in velocity over the time interval we're looking at. Symmetry. What does symmetry have to do with area in the plane? Well, it turns out that if we look, let's look at an interval from negative a to positive a in the plane. If our function is even, here's a graph of an even function, and we integrate the same distance to the left of 0 as we do to the right of 0. Because we have an even function, we know that it is symmetric to the y-axis. Everything that's going on to the right side of the y-axis is a perfect mirror image of everything that's going on to the left side. So we know that a property of a definite integral for an even function is that we could just take half of that area, either half. Here's the example of just taking the half from 0 to the right endpoint of A, and we could take twice that area, and it would be the same as all of the area from negative a to positive a. And that's an attribute that we can count on for an even function because it's symmetric to the y-axis. So that's what this symmetry in the definite integral is trying to tell you. For odd functions, it turns out that if we integrate from negative a to positive a, that because it's odd and because it's symmetric to the point of origin, we will always have the exact same amount of negative area as we do positive area on an interval that goes the same distance. Again, we're going the same distance to the left of the point of origin as we are to the right of the point of origin. So if on an odd function we are integrating from negative a to positive a, and we know f is an odd function, then we are guaranteed that that signed sum will accumulate to 0. And that's what symmetry has to do. Those are properties of even and odd functions in the definite integral. So you could use that as well. All right, so let's work this example. Hopefully we'll get through with it here before the end of this video. We measure the speed of a bobsled at 1 second intervals as it begins its run. A says, what is the bobsled's approximate acceleration when t equals 4 seconds? Well, we can approximate the slope of the tangent line because on velocity, that's what speed is, that's the absolute value of velocity, right? The slope of the tangent line is acceleration. So this is just a fancy way of saying approximate the slope of the tangent line at t equals 4 seconds. Well, remember, we do that by going to points on either side and finding the slope through there. So the acceleration at 4 is approximately the difference in the outputs on either side over the difference in the inputs. 30 over 2. So 15, and we have units. We have miles per hour and we have seconds. Acceleration is miles per hour per second squared. So let's see, we're not going to get through part B here. So there will be a third video. It'll be a short one. We'll do this Riemann sum, so look for the next video.